What we're going to start talking about now is the shapes of molecules. So this is all going to be starting from the PowerPoint, actually, of 2.2. So up until now, we've dealt with just the connectivity of atoms inside molecules, but because we exist in, at least in a physical sense, 3 dimensions, that means that the molecules that make up our universe have to have at least those 3 dimensions, and we need to figure out how that works. Now, the first sort of hypotheses of these were all theoretical and done, again, towards the end of the 1800s, like a lot of this other stuff we've looked at, and not verified until significantly later when the technology existed to look a little bit closer at molecules. It turns out that they were mostly right, so it's really interesting. So the theory that we are going to be working off is something called valence shell electron pair repulsion, VSEPR. You will usually hear it referred to as VSEPR theory, and not VSEPR theory, rather, but VSEPR theory. And the reason is VSEPR just sounds better than VSEPR. That's really it. But the idea in VSEPR theory is that when I have multiple atoms bonded to a central atom, so for example here, right, there's 2 electrons, right? These electrons here are near each other, and they repel each other because they're all negative. And so molecules are going to adopt a geometry that minimizes that kind of repulsion. So basically, what shapes can we build where those electron pairs are as far away from each other as possible? So I'll give you an example. When I have a central atom that is connected to 2 things only, right, the furthest away those 2 things can be is 180 degrees. And so we see that in BCl2 or in carbon dioxide. And it doesn't matter in the case of a double bond. There is some effects of double bonds that we'll talk about in a little bit later. But well, as long as, in this case, the 2 double bonds are the same, it doesn't really matter. The furthest away they can be from each other is 180 degrees, and that geometry is linear, right? It makes sense. It's a straight line. Right. Now, discard. All right. Now, here. So now we've got linear, right? So this is the simulation. You can watch this or you can go play along if you like, whatever you would like. Now, if I add a 3rd atom, all right, the geometry now looks something like this, and the bond angles are 120 degrees. And the way you can imagine this, it's a little tricky to see, I guess, but that you have the central atom in the middle, and each of the other atoms bonded to it make up the corners of an equilateral triangle, right? And the name for this shape is trigonal planar, which is fancy for flat triangle. Right, that's really what it means. So if we look a little closer here, you will see, right? So if we take the case of BF3, right? This is not a great triangle, but the fluorine atoms make up the corners of an equilateral triangle, and the bond angle is 120 degrees. So again, keep them nice and far away. Now, when we get to something like this molecule here, where we've got a double bond, things are a little bit different. So in this molecule, this is formaldehyde. You don't need to know the name. If you ever did a dissection, like sheep's eye or something, or a frog, or you've been into an anatomy lab, that's the smell. This is used to preserve tissues that were once living. Now, if we think about our theory of VSEPR theory, which is valence shell electron pair repulsion, here I've got 4 electrons versus 2 and 2. So I can assume that the 4 electrons are going to repel more than the 2. So that means kind of this bond is going to push away the 2 hydrogens more than these two will push away each other, so that the H's are going to get squeezed away from the double bond. And that's what we see in the actual bond angles here, where the OCH bond angle is about 122, but the HCH is 116. Now, there's something that's worth pointing out here in terms of knowing stuff. So the names of all the geometries you're going to need to know, as well as the sort of normal bond angles, right? So that this, if in a regular trigonal planar molecule, this is 120 degrees. I also expect you to know that when it's not, say, a normal or symmetrical molecule, that there's going to be some deviation from the ideal bond angles. However, I don't expect you to know, in most cases, what those deviations are, because they vary from molecule to molecule, right? If there was something other than a hydrogen here, these bond angles would be different. What I would expect you to know is that because there's a double bond here, that this bond angle is greater than 120. That's what you would need to know, that this is greater than 120, and this one down here is less than 120. I wouldn't expect you to know the exact bond angles, but I would expect you to know that there is some deviation. Now, the last one that we're going to talk about today is when we actually have to start getting into 3 dimensions, because so far we've had, basically 2-dimensional molecules. But when we add in a 4th substituent, a 4th molecule, we have to break out into 3 dimensions. And next class, we're going to talk about how do we bother drawing these, or how do we go through the trouble of drawing these when we don't have fancy computer programs. So if we were to stick this in 2 dimensions, right, the best we could do is have so the best we could do, as I mentioned over here, is that they would be 90 degrees apart. Not fantastic, but if we adopt a tetrahedral geometry, then we can actually get them further apart. So a tetrahedron is basically a 3-sided pyramid. And we have each of the atoms bonded to the central atom at the corners of that pyramid. And there you go. So this is known as tetra. All right, so this is a reasonable approximation of what's around the carbon. So if we have the carbon in purple and the stuff bonded to it, the shape is a tetrahedron. Now, when you're drawing in chemistry, what becomes important is simplicity. And there's a few conventions that we use, all right? So the first thing is that we want as many atoms as possible to be in the plane of your page, right? So there's lots of ways I can draw this, right? Like this anyway, because in reality, this molecule moves around. But to make my life simpler, I'm going to try and draw this with at least 3 atoms in the plane of the page. So I have this central atom and then these 2. And it doesn't have to be these 2. It could be any 2, but these 2. So these are all kind of in the plane of the page. And then this one here is coming out in front, and this one is in back. So I'm going to see if I can. Yes, this should work. Please. All right, excellent. So if I have the purple is my carbon atom, right? And then I have my hydrogen. That's not very good. So I want to remind you, those of you who are nervous about drawing or whatever, the bar is very low. Just so you're clear on how this works. The bar is super low, right? You can see that I, especially in this kind of online situation, not very good. All right. So that's the one going up over here. Then I'm going to do this one going down like that. All right. And then to do the one coming out in front, what I'm going to do is make a wedge like this with the sound effects. Those are required. Right? And you can color it in or not. It doesn't matter. Okay. So there you go. Then there's one in back there, and the way I'm going to do that going in the back is I'm going to make these little marks, kind of sideways dashes like that. All right, and that is how you draw a tetrahedron. Now, this is obviously not the molecule actually that we have, right? I've got and we're not going to worry about the structure of the OH right now. So that's, and then so this angle is, right, it's about 109.5. What about the sort of COH angle? And that's a great question. So if we, I'm just going to redraw the molecule. So if we look at our Lewis structure again, which was, oh, I got to share the screen, sorry. All right, so if we redraw the Lewis diagram of this molecule, like this is our Lewis diagram. And Cam, I'm not sure what you mean by the extra H atom. So this is the Lewis diagram that we started from, right? Now, here's the deal. When we have multiple atoms where, so geometry is something we care about when we have an atom bonded to more than one other atom, right? So this carbon is bonded to 4 other things, so we care about the geometry. The hydrogens, they're each only bonded to one other thing, so we don't care about that. This oxygen has 2 atoms bonded to it, and it has 2 lone pairs. So the question is, and someone can add this in the chat, is how many electron groups are around the oxygen? Nope, not 2, 4. All right. So here's the deal, right? 1, 2. When we talk about electron groups, so this is where the language matters. Yeah, 4. That's right. So this is where language matters. Electron groups and electron pairs are not the same thing, right? When we're talking about geometry, electron groups are anything that has electrons on the bonded, connected to that atom, right? So it could be atoms that are bonded, or it could be lone pairs of electrons. So in this case, this oxygen has 4 electron groups, all right? And 4 electron groups means tetrahedral. I'm just going to say tet because I can't write really well, right? And and this is something we haven't quite talked about in class, the lone pairs take the place of the of other atoms. So the shape that we actually observe is a derivative of the tetrahedron. So, but the key thing is that when we're drawing a molecule like this, we basically have to treat each of these things independent. Like we treat the carbon and then this. So if I want to draw this in 3 dimensions, what I'm going to do is I have the carbon atom, right? And it's a tetrahedron. So it looks something like that, right? H and H and then H. And then here's the oxygen. Now, the oxygen is also derivative of a tetrahedron, which means the bond angle between the O and the H is going to be about related to 109.5. So I'm going to put it something like that. And we don't actually have to show the lone pairs, right? This bond angle is actually going to be less than 109.5, and that's something we're going to talk about actually right now. So does that answer your questions? I hope. So what I want to jump to now is where we were on this. So I'm just going to change what I'm sharing with you guys again. All right. So, all right. So this is where we ended up last time, talking about a tetrahedron. Now, there are, so and I'm just going to go through a few of the other basic shapes. So we saw linear, trigonal planar, tetrahedral. Now, there are situations where it seems like there may be more than 4 things bonded to an atom. All right. So, for example, PCl5 is a compound. Now, it turns out that the bonding in PCl5 is really complicated in terms of what's actually going on, and we don't really need to worry about that so much. But what we do need to realize is that we can still use VSEPR theory to actually predict what the geometry of PCl5 is and molecules like it, and it works. The concern always here is that if I were to look at the Lewis diagram of PCl5 and I count, right, 2, 4, 6, 8, 10. So I have an expanded octet. This is the phosphorus is hypervalent, which is kind of a no-no, but it's also not a catastrophe either in this case, because we can still just use VSEPR theory to predict the geometry without worrying about how complicated the actual bonding situation is, right? But basically what we get is something called trigonal bipyramidal. It's kind of like, oh no, I don't have a good picture of it. What you can imagine is there's 2 3-sided pyramids that are stuck upside down, right? And what's interesting about this one is this is the only geometry that's not symmetric, or it's asymmetric. There are 2 different positions. The chlorines here and here are what we call axial. They're on an axis. And then these ones here, these positions are around the equator. They are equatorial. And so there's 2 different bond angles. There's this one, the equatorial bond angle is 120, and the axial to equatorial bond angle is 90. There's one more parent shape that we're worried about, which is octahedral, where we have 6 things around a central atom. And it looks kind of like this, right? 2 4-sided pyramids stuck upside down on each other. That's an octahedron. Now, I mentioned this early on when we were talking about, sorry, I'm going really fast here. Yeah, when we were talking about something like formaldehyde, where because there's 2 electron pairs here, there's 4 electrons, there's more repulsion between the this and this than down here. So the 2 hydrogens kind of get squeezed together. Now, people often get fooled in a situation, say, like with nitrate, because when we draw Lewis diagrams, it looks like there's a double bond and 2 single bonds. But we know, based on going over this a bunch, that in fact that's not the situation, that there's resonance between these, and these are all 1 1/3 bonds, even though I didn't draw them that way. And so, in fact, in something like nitrate, what we observe is that the bond angles are all equal. What happens when we have lone pairs? All right. So if we take the case of, say, ammonia, NH3, all right, the lone pair, so if we count, there are 4 groups connected to the nitrogen atom, the lone pair, and the 3 hydrogens. So the electron geometry is tetrahedral, because 4 things means a tetrahedron. But if we actually look at this molecule using, say, electron microscope, scanning, tunneling microscopy, atomic force microscopy, all these ways of looking, we don't actually see electrons. They don't stick up in a way like this. Really, the lone pair is kind of smooshed onto the surface of the atom. What happens is that the lone pair repels, because the density of the electrons is really close to the surface of the atom here, or it is kind of the surface of the atom, if you will. It repels a lot. So what happens is, the first thing is the molecular geometry, which is kind of the geometry that we observe, is trigonal pyramidal. So trigonal pyramidal is a derivative of tetrahedral, right? And what happens to the bond angle is that all the hydrogen atoms kind of get squished together, right? So in a perfect tetrahedron, the bond angle is 109.5. In the actual geometry of ammonia, the bond angle is 107. Now, this is really important. In terms of what I expect you guys to know, right? I need you, the bond angles from the 5 parent shapes that we learned, linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral, you need to know those ones, all right? In terms of the bond angles in the derivative shapes, right, when we have lone pairs, you only need to be able to tell me the bond angle is going to be less than or greater than the ideal, except for ammonia and water. So ammonia, you need to know that this bond angle is 107, all right? In the case of water, the effect is exaggerated. So there's still 4 groups on the oxygen, so it's a tetrahedron, but when we look at it, the shape we observe is just bent. That's it. And the bond angle here is 104.5, right? So that's the other exceptional bond angle that you need to know. If I asked you, what about say H2S? So H2S is similar to the Lewis diagram of H2S is basically the same as water, right? So if I said H2S, what I would so the sulfur should be tetrahedral. This bond angle, I don't know what it is. Well, we're going to talk about it a little later, actually. But all you would need to be able to tell me is that it's less than 109.5. All right. It's not one that you need to know. So here's the sort of the general theme of this is that when you have no lone pairs, you have roughly ideal bond angles. And then when you have one lone pair, the bond angles are reduced. And then the more lone pairs you have, the greater the reduction. Right? So that's for tetrahedron. The same is true for trigonal planar. Now, when we get to these other shapes, all right, there are more derivatives of the shapes. And so the truth is I don't have a good way to learn this except to memorize it. Mess around with the PhET simulation. It's a really good way to get used to those shapes. If you have a model kit, then that is maybe the best way. So when we get to trigonal bipyramidal, because the shape, remember trigonal bipyramidal, the shape is not symmetric. So the repulsion here, which position gets replaced? Because you think about it, if we go back here, it doesn't matter which of these in a tetrahedron, all the positions are equivalent, right? There's a symmetry, if you remember back to whatever high school geometry, right? There's rotational symmetry in this molecule, so all the positions are geometrically equivalent to each other. That's not the case in something that's trigonal bipyramidal. But what happens is the axial lone pair isn't what happens because that has more repulsion. So what we get is replacement of the equatorial lone pairs. So one and then so on. And the geometry here is called seesaw. I don't have a good picture of it, but if you turn it on its side, it looks a bit like a kid's seesaw. And if we take something like this, where we've got still 5 groups on the bromine, but 2 of them are lone pairs, it's still trigonal bipyramidal, but it's T-shaped, the geometry. And then if you have 3 lone pairs, it's linear. Again, there's not really a good way to learn this except to try and memorize it. If we're going to octahedral, so the bromine here has 6 groups around it, and including a lone pair. And in the case of an octahedron, it doesn't matter because all the positions are symmetric, and we just replace one, and we get the geometry is square pyramidal. And then now in this case here, XeF4. Now, noble gases, they do react, just not a lot, right? So in this case, what happens is in order for the lone pairs to be as far away from each other as possible, they're on opposite sides, and we get a geometry that's known as square planar. And then then I guess we kind of could keep going, but I don't have any good examples of it. So that was really fast. This is one of the examples in the problem set, glycine. But the idea, here is that when we have lots of interior atoms, we basically just have to treat each of them separately. All right. So we go and we look at each atom one at a time. So the nitrogen has 4 electron groups, right? It's connected to the lone pair, hydrogen, hydrogen, carbon. So this one is tetrahedral trigonal pyramidal. Then this carbon is connected to 1, 2, 3, 4 things, so it's tetrahedral. This carbon is connected to 1, 2, 3 things, so that's trigonal planar, and then the oxygen is tetrahedral bent. And kind of draw each one, and you want to sort of connect the dots, connect them all to each other. The key thing in drawing these bigger molecules is that you want to get as many atoms as possible in the plane of the page. And typically, these atoms here make up what we would call the backbone of the molecule, and those ones, we're going to try and get them all in the plane of the page. And so a fancy drawing might look something like this. More than one bond in a molecule, right? And we start paying attention to geometry. So for example, if we look at carbon dioxide, it has 2 polar bonds, right? The carbon-oxygen bonds are polar. But because it's linear, the 2 vectors cancel each other out. And as a result, carbon dioxide is not polar. Water, in contrast, is polar. And this is because the 2 vectors don't cancel each other out, right? In this case, the hydrogen and oxygen bonds are polar, but they point from the hydrogen towards the oxygen, and we can add them up tip to tail to make a resultant. When we add up vectors in this class, we are eyeballing it. We don't need to really show, we're not doing any trig. We're just trying to do it by eye to get a general sense. And when we look at the electron density map of water, we see that there's a partial negative, around the oxygen, and the hydrogens are partially positive. So why does polarity matter? The big reason is that polarity affects all kinds of things: boiling point, solubility, and so on, right? So opposite charges attract or each other, like charges repel each other. So for example, water is polar, and oils like olive oil or whatever are non-polar, and so they don't mix because of this polarity difference. We talked about polarity already in class, right? We talked about it in simple molecules like something like HCl, right? So hydrogen chloride, when it's not dissolved in water, it's a polar compound because the chlorine is more electronegative than the hydrogen, right? And so if we do an electron density map, what do we see? There's a lot of electron density around the chlorine and almost nothing around the hydrogen. So there's a partial negative around the chlorine and a partial positive around the hydrogen. And this is called a dipole moment, and it's a vector quantity. Now, the thing is, this gets more trickier when we start introducing